Okay, so I discussed the Poisson distribution last time. Now let's look at this distribution uh, from a different point of view. Well, we can look at this from many different points of view. In fact, this is related to Poisson process. Uh, so, well, this theorem says that a limit of a binomial distribution with n and lambda over n as p is in fact Poisson lambda. Now, what is lambda over n? So I said lambda is average number of people arriving per hour. Now this, you can talk about lots of things, like when you call some place and they put you on hold, that is a Poisson process, not just Poisson distribution, Poisson process in fact. That company can say plan on this. Say, okay, the average number of people who call this place is like 20 per hour, something like that. So that is in fact that has to do with Poisson distribution. So when I said people arriving, just think this can happen in many different contexts. Like, and it might have happened to you a lot when you call some place and they say, okay, the line is busy and please wait, and they they just sing a song for you or something like that. So now let's look at it this way. So I have a 1 hour period 1, and I know that there are lambda number of people arriving in average. Now I can find some small time interval, very small, such that in this time interval only at most one person arrives, no more than one. Okay, so this is my assumption that I can find in fact a small time interval. Just make it smaller. So no, I think it's 2. Okay, smaller. 2, no, smaller. So this is becomes infinitesimal in fact. But anyway, so let's divide this by some n, such that when you divide this by this number of subintervals, so that's like n now, n subintervals. So this starts with 0 and at n, say, these points, such that each subinterval is less than that time period that I found. So if I found that the time period is 0.000001, for example, and in this small time period only at most one person arrives, then I choose n to be, what was that, 10 to the power something, so that it divides that this time period 1 into like 10 million or whatever that was, subintervals. Okay, so as n goes to infinity, it gets larger. So I have no problem when I find that n such that in each time period here, at most one person arrives, then I'm okay, because if n gets larger and larger and larger, smaller time period will no more than one arrives. So this also gives me something else, that it's like a probability. So what is the probability that one person arrives in one of these time intervals? That probability is in fact lambda over n, right? So let's fix n. So that probability is like lambda over n. So what does it look like now? I have n positions, say n, and the probability of success is 1% arriving. So the probability of success is lambda over n. So if I divide this time interval by some n, very large n, I have small time intervals here, and I can assume that in those small time intervals, at most one person arrives, 0 or 1. So if I look at it from a different standpoint, this looks like a binomial process. I have n positions, or it's like I'm tossing a coin, for example, something. And success means one person arrives, and failure means nothing. No one arrives. What is the probability of success? Is lambda over n. So if I look at it this way and fix n, then it looks like a binomial. It is in fact a binomial with n, say, trials, and the probability of success in each trial is lambda over n. So now this theorem says as n goes to infinity, this process becomes Poisson lambda. Now how does this happen? So in fact I have to prove that the PMF here becomes the PMF of Poisson lambda. So let me write down the PMF for this one. So what was the PMF for binomial? So I have to prove this. Limit as n goes to infinity. What was that? Nx lambda over n to power x, 1 minus lambda over n to power n minus x is this, e to power minus lambda, and this is for 1 hour, okay? Because the period of time was 1 hour, so it's for 1 hour. 1 hour. So that's minus lambda times 1. Times lambda to power x over x factorial. So I have to prove this. Okay, let's look at this and see if I can kind of bring this out of this formula. Let's write this down in the more expanded, so that's n factorial over x factorial n minus x factorial. I have an x factorial here, x factorial, lambda to power x is here, right? I have a lambda to power x here, so let's write it lambda to power x times 1 over n to power x. And where is e to power minus lambda? Well, it's here, this one. 1 minus lambda over n to power n. And then what remains is 1 minus lambda over n to power minus x. Okay? So okay, so I have x factorial here, I have lambda to power x here, and I have this. What is this? From Calc 1, I guess, or Calc 2, I can remember one of them. This is e to power minus lambda. So, in fact, the limit. So let me erase this and write up here, and so this has nothing to do with n, and this also has nothing to do with n. So I can move them out of the limit, lambda over x, lambda to power x, x factorial. Then I have a limit here, limit on top I have an n factorial, denominator n minus x factorial. I have this one and this one remaining. 1 over n to power x and this one. 1 minus lambda over n to power minus x. And this n goes to infinity, times the limit of this, times the limit as n goes to infinity of 1 minus lambda over n to the power n. You can use like L'Hopital's rule, for example, because that's 1 to the power infinity. That is an indeterminate, and you can use L'Hopital's rule, and you will see that this is in fact e to the power n minus lambda. So I have e to the power minus lambda times lambda to the power x factorial, and inside I have something. So let's look at the inside. Let's look at the inside. The inside I have a limit n goes to infinity, and I have n factorial, n minus x factorial, and this is to the power minus x, right? So this will be n 1 over n to the power x, and this will be n minus lambda to the power x minus xa over n to the power minus x. So this one and this one cancel out, 1. And this one comes down here. So I have e to the power minus lambda x over x factorial, limit n goes to infinity of n factorial on top, n minus x factorial times n minus lambda to the power x. Now, let's cancel things here, because that n minus x factorial and n factorial, so many things cancel out. And this becomes this e to the power minus lambda x factorial, limit n goes to infinity. On top I have n times n minus 1 up to n minus x minus 1. You see, this starts at n minus x, then goes to 1. And the next one here is n minus x. And that cancels with this. And in the denominator, I have n minus lambda times n minus lambda x times. And how many terms do I have here? X. So number of terms on top is x, number of terms at the bottom is also x. Now what do I have here? I have n minus something. I have n minus something. Each one of them is n minus something. So I can, if I look at this limit is like this. The limit is like limit as n goes to infinity of say, how should I write it? So yeah, let's write the first one, n over n minus x times the limit n minus 1 over n minus x, n goes to infinity, and the last one is limit n minus x minus 1 over n minus x, and then goes to infinity. Okay, so this is 1, right? And they have a coefficient 1. Remember from calc 1, this is 1, 1, 1, 1, 1. So this limit is 1. This limit is 1. And what have I proved? I have proved that this limit of this thing is in fact simply equals to what was that, e to the power minus lambda to the power x over x factorial. This rest, this is 1. This is 1. So we proved that this thing is 1. Okay, so the Poisson distribution, in fact, we have proved that it is some kind of limit of a binomial distribution. So it's like as I said, limit, and you will see that this binomial distribution is also related to normal distribution as a different limit. So a different limit of this thing somehow will give me normal distribution. So, and I mentioned at the beginning that this distribution is crucial in one way. This is one way to approach Poisson distribution. But anyway, so that was one way of describing this thing. Okay. So next I will give you another interpretation of this.